This okay. So I welcome you all intellectual adventurers in today's meeting. So today I'll be talking about kind of mathematical topic that will take us from natural numbers all the way to Clifford algebras. So let us start our journey. So this is the brief outline of this talk. So first of all, I'll say a very few words about the relation or strong intimacy between mathematics and physics, as we all know about it already. And then about the hierarchy of numbers, starting from natural numbers to integers, rational numbers, irrational numbers, reals, complex numbers, and hypercomplex numbers. So as I just said, so I'll first talk about the real numbers, then the complex numbers, hypercomplex. So hypercomplex numbers would include quaternions and octonions, and we will see what these numbers mean. And then we will ask a question: are there any further? So one answer is provided by Hurwitz's theorem, as we will see later. But uh, if we take out some restrictions, then we see that even higher dimensional extensions are possible. So those are Clifford algebras, and we will see what are Clifford algebras later. And then finally we'll summarize. So first of all, let me say a few words about the very strong friendship between mathematics and physics. So it seems perhaps it is one of the wonders of natural world that the natural world is so agreeable to being described in the mathematical language. So it's kind of astonishing, and it was especially astonishing to Eugene Wigner, who was wondering about unreasonable effectiveness of mathematics and natural sciences. So some examples include, let's say, classical mechanics or Newton's equations and the equations of quantum mechanics, on which literally all human civilization is based. So those are very beautifully written in terms of just, I mean, very small equations. So in this, various different numbers have a very great role to play. So as we will see what those numbers are and what role do they play. So starting with, so let's start with the usual natural numbers. So natural numbers allows us to count different things. So let's say 3 sheep or 4 apples or maybe 5 cows, 20 what perhaps mangoes, etc., etc. But as the need increased, we needed even more sophisticated kind of numbers. So we needed to introduce Z, which is the symbol for integers. So here N is the symbol for natural numbers. Here Z is the symbol for integers, and the rationals. As we will see what rationals are. Perhaps you already know, but I will talk them about anyway. So starting with, so one example of one very simple example of integers can be, let's say you because of some reason you lost all the money, or maybe it might have happened in the earlier time also. So because of some reason a person lost all his money, and he does not have any money now, and now if he goes to some other person to lend him some money, then the person has effectively negative balance. So his the person's money is in a way negative. And how do the rationals come about? So let's say you want to share your half pizza with your neighbor. So here I've shown the full pizza, and you can take 2 pieces, one for you and one for your neighbors. So this is where the rationals come into picture. So formally we say that p over q, or we rather represent a rational number in the form of p and q, p over q, where q and p are both integers and q is not equal to 0, and they also should not have any common factor. So for example, if you say, let's say 3 over 6, so 3 over 6 is the same as 1 over 2, because they should not have any common factor in them. So it also means that if you write p over q, then either p or q has to be an odd number. So one of them has to be an odd number, and another one has to be an even number. They cannot be they cannot be even together, or they can also be odd. For example, 5/3 will also work, but they cannot be odd simultaneously. Okay. So it seemed that nothing beyond this was necessary. So yeah, so why would you need anything beyond, let's say, a quarter pizza, or if you can say that, or maybe negative money, or if you can count things. But no, that is not true. So when these numbers came into picture, so for example, here I've shown a right angle triangle with sides 1 and 1. So you know that this diagonal length is square root of 2 by the simple Pythagoras theorem. And there's one more example. Let's say this is the circle with its circumference c, and d is the diameter. And then it always turns out that the ratio of the circumference to the diameter, irrespective of the fact how big or small the circle is always a fixed number, or always turned out to be a fixed number, and that fixed number was pi. But pi is not a rational number, so it cannot be written in the form like p over q. And there are various proofs available on the internet. So here and here we will see like the mathematical reasoning to show that y square root 2 is not a rational number. Okay, so these are, as we call them, as these are irrational numbers because they are not rational. So perhaps irrational is a kind of abuse in my opinion, because perhaps it means that they were not understandable at that time, because everything should be written in terms of some kind of length, because perhaps it is impossible to measure a square root of 2. Okay, I should not say that, but uh, but at least it is not it cannot be written in terms of integers or their ratios. So thus, if you include rationals and irrationals together, then you get a set of real numbers. And a lot of work by mathematicians have been done on various properties of the real numbers. So the real numbers have all the nice properties that one would ask for, and we will see what those properties are. So as is the usual goal of mathematicians, so they would start with some basic axioms, and they would try to prove everything based on those axioms. So as we will see, the real numbers form something called as field, uh, some algebraic structure that is called as field, and that field satisfies some basic properties, and all the properties of real numbers can be proved on the basis of just those 9 properties. So now let's see how do we prove that square root 2 is irrational. So this is a very spoon-feeded like of kind of proof. I mean, I've really very simplified it. So but of course it is based upon the reason that we usually learn, let's say in our first year undergrad course, or maybe before that. So this is how it goes. So we will use a proof technique known as the proof by contradiction, or in other words, reductio ad absurdum, which is one of the favorite tools of mathematicians. So what does it mean? That we will assume that, let's say, it is rational, and we will reach a contradiction. So yes, so in that spirit, let us say that there exists a rational p over q such that p over q is equal to square root of 2. So if I square on both sides, I'll get p square equals 2q square. So since p and q are integers, they can be negative, they can be positive, but all in all, I have 4 possibilities. So p and q are both odd, p and q are both even odd, odd even. So I can only have these 4 possibilities. But because of p square equal to 2q square, so q can be anything. Q can be even or odd, but since it is getting multiplied by 2, so p has to be always even. So these 2 are ruled out. So these 2 cannot be true, because p can only be even. And now one more thing. So since p is even, I can say that p is equal to 2r for some integer r. R can be even or odd, that doesn't matter, but still p would be equal to 2r. So this, if I put it back here, I get q square equals 2r square. So since this is true, then so Q cannot be odd. So this is also ruled out. So I have only one possibility, this even, that P and Q both must be even. But then they cannot be even also, because by definition, I have got a rational which don't have any, so P and Q should not have any common factor. So yeah, so for example, if it was 6/4, so then it should have been 3/2 instead. So I'm assuming that P and Q are even. I mean, so I'm concluding this P and Q are even, and P and Q, but P and Q cannot be even. So I'm reaching this conclusion. So if I assume this, I'm reaching a conclusion that P and Q are even, although they should not have been even. So I'm reaching a contradiction. So so let me say that again. So when I say this is rational, I'm already assuming that P and Q don't have common factor. So if P and Q have common, if P and Q are even, then they would have common factor. So that's a contradiction. So this means that square root 2 cannot be rational. So it's an irrational. So now, so after discovering, so let's say starting from natural numbers, integers, rationals, and then finally rationals, so everything is taken care of. So I can say some positive distance, let's say whatever it is, square root of pi over 2, square root of 2, anything I can write in terms of real numbers. So that can be positive if you go, let's say, on the positive side of the x-axis, or whatever you call it as, and you can also have negative numbers. So the reals, or the real field as we call it in mathematics, satisfy these following 9 properties. So given for any, so I mean, of course I will not go through them because these are not very useful for the purpose of this talk, but in order to for the sake of completeness, so for any x, y, z and r, these properties will be satisfied. So you can remember these properties by this mnemonic, can E D. So here C, commutativity over addition, A, associativity over addition, existence of neutral element, which is 0 here with respect to addition, and I means inverse. So for every x, you must have minus x, so that if you add x and minus x, you will get 0, and this will always happen for the case of real numbers. So although they might seem very obvious, yeah, of course everyone knows this, but this is not. So the spirit of math is you start with some very basic properties, and then you can and then you can build upon all those very simple properties and literally prove everything about real numbers. And then second, KNED is because of commutativity over multiplication now, associativity and existence of neutral element, but now with respect to multiplication. So here it was, so here you add, here you multiply. So there must exist some neutral element 1, so that if you multiply by x, where x is any real number, then you must get back x. And you must also have an inverse element which satisfies this condition. So for every x which is not 0, there must exist y such that xy is equal to 1. So y is the inverse of x in this case. And you also must have the distributivity. So by using these properties, you can literally prove everything about real numbers. Okay. So as I said that, so real numbers have,
I want to ask one thing about that existence of inverse with respect to addition. So xy equal to 1, so how is it is addition?
Sorry,
in
in
which
which
case?
case?
The second last.
Oh,
Oh,
sorry, it
sorry, it should have been multiplication.
Okay.
Sorry.
Thank you. It should have been multiplication. Yeah, there is an error here. It should have been multiplication. Thank you.
Thank you.
Okay, no problem. I was thinking that it should be some addition, and I'm not able to understand.
It was multiplication. Thank you. Okay. So so now, so real numbers satisfy some very important property that that they satisfy that they are commutative and associative over addition as well as multiplication. and they also have well-defined norm. So norm, let's say, of -1 norm is equal to 1, and and based on this, apart from, let's say, 0, which is also a real number, you can always divide one number by other. Of course, that the other number should not be 0, and hence its inverse also exists. So you can divide any number by any number. So a clear notion of division is defined. So mathematicians will also call it as that this is an example of norm division algebra. But I mean, we don't have to go into the details of it. So, but there is one more property. So real numbers have one very important and inherent property, that they're ordered. So given any two real numbers, only either one of these conditions must hold. Either A is equal to B, either A is greater than B, or either A is less than C, or A is less than B. But as we will see that this condition, the order property, will not in general hold for higher dimensional cases. Okay. So, but so it seems now my work is done. I can do everything with real numbers. Why I don't want to go beyond real numbers? Why do I have to go beyond real numbers? But it turns out that's not true. So you just look at a very simple equation, x square plus 1. So it does not have any solution, any real number solution. So this equation will not be satisfied by any real number. So it seems that we have to go beyond real numbers. So this led to the introduction of the so-called complex numbers. Of course, complex numbers are not that complex. They have very beautiful math. The complex analysis, yes, it is very beautiful. So complex numbers can be written in the form of a plus ib, where a and b are real numbers. So as we all know now, that this equation has a solution plus or minus I, where I is equal to square root of -1. That's it. So and there is an important result known as the fundamental theorem of algebra. So that was proved by Carl Friedrich Gauss. So that shows that you can have any sort of this kind of equation. So this is a polynomial equation of nth degree, because you have n is here, and these are complex coefficients. So this equation will always have solution on the real field, and there would be at most n solutions. You cannot have more than n solutions. That's first thing, and you will always find solutions, howsoever, and there will always be solutions over the complex field. So this set, I mean, the numbers of this form form a set. So this is called the complex numbers, and it is also again a field. So it satisfies all those 9 properties that we listed before in the previous slide. But an important thing to be noticed here is that it loses the property of order. So there isn't any obvious notion in which two complex numbers, let's say you have two complex numbers, z1 and z2. So how do you say that z1 is greater than z2, or z1? Of course you have the notion when z1 equal to z2, but you cannot say what is the meaning of z1 is greater than z2 or z1 is less than z2 for any given two complex numbers. So although we kind of went from real numbers to the complex numbers, and complex numbers, as it turns out, are very useful in physics as well. I mean, of course they have many other applications, but in physics also they are very useful. But we have lost this somehow property, that we have lost the order property. There is no order now. There is not an obvious notion. Of course we can define order as well, but there is no obvious notion as was there in the previous case. So but yes, we are willing to sacrifice this property for the sake of applicability, as we will see that the complex numbers have a lot of beautiful applications in physics. I mean, I'll talk about the physics examples. So complex numbers are literally everywhere. So one very trivial example would be the plane wave solutions of source-free Maxwell's equations. So they admit solutions of the form exponential I k dot r minus omega t, where omega is the frequency, k is the wave number. And also the Schrödinger equation of quantum mechanics. So you can see I is sitting here. So I is here. So and this is very important. So since semiconductor devices work on the principle of quantum mechanics, so literally the whole human civilization works on quantum mechanics and hence on the complex numbers, because you have I here. So in that sense, complex numbers are everywhere, in your computer, in your watch, in literally everything you see around. So and one example would be that it also appears in, for example, signal processing, or in Fourier series, also Fourier transforms, which have applications in solving the partial differential equations. So now the question is it possible? So we started from real numbers which were in one dimension. So as we know that complex numbers can be represented on the Argand plane. So the complex number a plus ib can be represented as a point on the Argand plane or the complex plane. So we went from one dimension to two dimension, and we got a lot of new things, got a lot of new applications. So now the question is it possible to extend complex numbers to higher dimensions, and do we get any more applicability? Let's see what happens next. So this question leads us to quaternions. So quaternions are kind of natural generalization of complex numbers to higher dimensions. So complex numbers are two-dimensional, quaternions are four-dimensional, in the sense that I will describe now. So these were originally introduced by Hamilton, the Irish mathematician, I think Irish mathematician. So while he was looking for higher dimensional generalization of complex numbers of the form a plus ib. So these numbers were very useful, let's say in the beginning of by the beginning of 19th century. But after J.W. Gibbs invented the notion of vectors and associated dot and the cross product, these almost lost their significance. So I mean, apart from some very few places, they really don't appear anywhere because these vectors are very easy to apply in many situations. But now we will see what the quaternions have to offer. So one important property is that we at the level of quaternions we lose the property of commutativity. So quaternions are no longer commutative with respect to addition. So so let me repeat it once more. Real numbers were commutative with respect to addition. A plus b equals b plus a, or a into b is equal to b into a. And this was also true for complex numbers. So if a and b or z1 and z2 are two complex numbers, then z1 z2 is equal to z2 z1. But this is no longer true for quaternions. So for two quaternions, q1 and q2, q1 q2 is not the same as q2 q1. So of course we have gone to higher dimension, but we have lost this property of commutativity. So but they still satisfy commutative and associative law of addition. I mean, all those properties that were there, but for the addition case. And if we also assume that additive identity and the multiplicative identity, additive identity is 0 and the multiplicative identity is 1, if these exist, then we call quaternions as a ring with identity, this one.
What is the meaning of ring with identity?
So ring is just a mathematical object, some algebraic. So field is an object, for example, vector space is an object. Ring is also an abstract object or algebraic structure, if you like. So ring is not that ring which we wear in hand or rather in fingers, but ring is. I mean, I don't know why this word was used for this case, but this is what we use. Okay, so let me also say some more few words. I mean, so these are some of the mathematical details in order to make some connections with what the audience already know. So then any quaternion is expressible in terms of the basis, which is this 1 q1 q2 q3. So so instead of q1 q2 q3, you can think of 1 I j k. So in the case of complex numbers, you only have 1 comma I. but in this case you also have j and k. So again in this case,
Gyanti, can you mute yourself?
so in this case you have q square equals -1, because in the earlier case you had I square equals -1, but in this case, since you have, let's say q, or if you think of q1 as I, q2 as j, q3 as k, then I square equals j square equals k square equals -1. But and these also have additional property that I times j times k is equal to -1. So these are the two properties that that Hamilton needed in order to come up with this or complete the theory of quaternions. And he was so excited by this idea that he just carved it on what was the name of the bridge, on a bridge on Dublin, in Dublin, on some river, which I'm not able to recall right now. So I'll show this picture later. Okay. And but if you look at these constructs or look at these equations, these tell you a lot about how quaternions can be useful. So if we for the time being forget about R0, let's take R0 to be 0. Okay. So so I can think of this as the as a vector space over the field of real numbers. So here R0 and Ri are real numbers, and this is the basis vector, as usual is the case for the vector space. And this is and this and if you look at this, this is very similar to what the Lie algebra for SO3 is, if we can recall. So SO3 has three generators, three angular momentum generators, let's say Jx, Jy, Jz, and they also satisfy this kind of property. So there is a close link between the two, and thus quaternions can also be useful, or in fact they can be used for describing rotations. But vectors and like we have more developed machinery these days, so we don't really use quaternions very much. And so and in this case also we can define a multiplicative inverse. So that will allow this to hold, q inverse equal to 1. So this in a way says that I can divide, or I can take the inverse of a complex number. So I can divide 1 by any given sorry, in this case it is quaternion. So this property was there in case of real numbers. Let's say if I have the real number pi, I can still get a real number by dividing pi, by dividing 1 by pi. So 1 over pi is also a real number, 1 over 2 is also a real number, 1 over 100, 2000, square root of pi is also a real number. And similar thing happened, and of course you should not divide by 0, and this also happened in case of complex numbers. So for any complex number a plus iv, where a and b are not both 0, then you can always divide by a plus iv. So 1 over a plus iv is always defined, so that is a minus iv over a square plus b square. And the same thing happens in case of quaternions. So for quaternions also you can do this. So if, of course, the quaternion should not be 0. So quaternion is not equal to 0 means that R0, either one of these should be non-zero. Either R0 is not 0, or Ri, R1, R2, R3, either one of these are not 0. Then you can divide by that quaternion. So so since again, I mean we have seen one example of ring. Oh yeah, this is the same thing. So quaternions are so quaternions are also an example of division ring, as I talked about before. Okay, yeah. So notice that in this case, so when we go from complex numbers, or when we were looking for the higher dimensional analog of complex numbers, we did not get dimension 3 but dimension 4. So as you can see, 3 for this and 1 for this. And this is what is written on the, I mean, so this is what he wrote: I square equals j square equals k square equals ij equal to -1. So this is what William Hamilton wrote on that bridge. Yeah, so his name was Sir William Rowan Hamilton. the full name was this. Oh, it does not say anything about the name of the bridge. Okay, and also the river. Okay, fine.
Rahul bhai,
Yes.
I think he the same person which name has been given in the Hamiltonian, right?
Yes. Yes.
Okay.
He's the same person.
Okay. Okay. Okay.
He has done a lot of work.
So, actually, can you tell something that what was he trying to solve for which he has come to this conclusion, this and which
Quaternions.
excitation he? Yeah.
No, so he was looking for higher dimensional analog of complex numbers.
Oh, I see. So
A plus IB.
multiplication of. Oh, I see. Okay.
Yeah, generalization of complex numbers to higher dimensions.
Okay. Understood. Like our what is that called? The differential we call in general theory of relativity. You used to often encounter that thing. What is that called? I'm forgetting here. That cap signature used to.
Sorry, I cannot.
Differential or I'm also. I could not remember that suddenly.
Forms.
Lost it. Anyway, huh? Farms, right? 1 farm, 2 farm, 3 farms, like that. Hello.
Okay, I'm not able to connect. Yes, but I have also read them. But in what sense they are? Oh yes, they are. I mean, okay, I'm not able to recall in what sense they are generalization of one-dimensional or the usual case, because forms are useful for a very elegant description or very elegant writing of the Maxwell's equation as well.
Yes.
So you have the operator, this the differential operator, and then the what? And the Hodge operator. Yes. So you have the Hodge operator and the differential operator. So one equation becomes
Yes.
star f equals 0, and one becomes dA equals star f equal to 0 takes care of the two source free Maxwell's equations. Divergence b equal to 0, and
right.
And what was the okay, I'm not able to recall right now. Fine.
Okay, no problem. I thought that you had the generalization of the differentiation in the higher dimension to be and this is the generalization of complex number in higher dimension.
Yeah, perhaps it is related to the Grassmann algebra. Whatever you are saying, it is somehow related to the. I mean, I have not included the Grassmann algebra, but I think it is related to the Grassmann algebra. I will only say some words, a few sentences about the Clifford algebra only.
Okay, so Clifford means Clifford is usually follow the usual commutation rule, but Grassmann thing I think Dirac has used.
Yes.
Right, anti-commutation rule.
Yes. Exactly.
Okay, right.
Yes, true.
Okay.
So now, one more generalization to even higher dimension is the octonions. So octonions, as the name is suggesting, octane, octet, etc. So it means 8. So as you can understand from the name, that octonions are kind of 8-dimensional numbers. So even higher dimensional extension of quaternions was tackled by John Graves, an English mathematician, in 1843. But it seems that Arthur Cayley, the famous English mathematician, already knew. Not already knew, but he rediscovered these octonions independently in 1845. So at the level of octonions, we lose the property of associativity. So you see what is happening. At the level of real numbers, we have all the very important cherished properties. But when we went to the complex numbers, we lost the property of orderness. So there is no obvious notion in which you can compare two complex numbers. But when you but still the commutativity with respect to multiplication was there. But when you go to quaternions, you lose that property as well. So if you have two quaternions, Q1 and Q2, then Q1 into Q2 is not the same as Q2 Q1. But here you also lose associativity. So I mean, you have to pay some price. You are able to make generalization, but you have to pay some price at some point of time. So this is an example of 8-dimensional. Okay, okay. So I will give an explicit construction that how it is 8-dimensional, and it is non-associative because we have lost this property. And again, division algebra, because we can divide by any non-zero octonion. But okay, so we'll ask one more important question after this. So they satisfy these mathematical property. So any given octonion which I am representing by O. So O is an octonion. Oh, I'm sorry. This should not have been 1. This should have been some complex number, some Z0. This should not have been 1. Okay. And this can be written as a linear combination of 1, O1, O2, O3, O4, O5, O6, O7. So you have a basis which has 8 elements. So any octonion can be written as a linear combination, as we were doing for complex number, as we were doing for quaternions. And oh gosh, this should be -1. There's one more error. So, and all these numbers, so all these all these, if you like vectors, satisfy this property also. So this is kind of generalization of I. So you have A plus IB in complex numbers. You have I square equal to -1. But when you go to quaternions, you have I, J, K. So that so similarly you have I square equals J square equals K square equal to -1. But in this case you have 7 of them. I, J, K, L, M, N. Let's say I, J, K, L, M, N, O. So J, K, M, N, P. Let's say P, because I've already taken O. So then I square equals J square equals K square equals L square equals M square equals N square equals P square equals -1. So this is what it is saying. And this also satisfies this anti-commutativity property and some more complicated properties. Like this is called as a cycling identity and also double indexing identity. So yeah, of course we are able to see this, that the higher dimension we go, the things become a bit more complicated, even more complicated. So these conditions were not there in the previous case, but now these so-called, well, generators, or let's just the vectors, will satisfy this property. So now the question is, are there any further, or will it ever end? So we started with real numbers, then complex numbers, then quaternions, then octonions. So are there any further? Okay, let me ask you this. What do you think? Are there any further?
It will be.
Well, answer is surprisingly no. There are no further such possibilities.
Why?
I'll explain now.
Okay,
I'll
great.
explain now. Okay. So Hurwitz's theorem, proved by the German mathematician Adolf Hurwitz, assures. So okay, of course there are, I mean, but we want to assure some properties that they should be intact, that we want to assure that we can divide by any such number. But if we are allowing that to just go out, that we are allowing possibilities where we don't have to divide by numbers, then there are possibilities. But if we enforce that we should be able to divide by number, then there are no possibilities. So it says that there are exactly 4 types of norm division algebra. So norm based modulus kind of thing. So let's say in case of complex number, if you have complex number Z1, its conjugate is Z1 bar. So let's say again, a complex number Z equal to A plus IB, and the conjugate is A minus IB. Then ZZ bar equals A square plus B square. So square root of this can be taken as the norm of the complex number Z, if you can recall. So it can also be done for quaternions, it can also be done for real numbers, it can also be done for octonions. So this property must be there, but if you want to keep this property intact, and also, so norm should be there, and you should be also able to divide by given number. So you can divide by real number, you can divide by complex number, you can also divide by octonions given that it is not 0. You can also divide by quaternion. So it says that this condition, so I mean conjugate in the sense that I've already spoken about. So this will only work for dimensions 1, 2, 4, and 8. So 1 is for real number, 2 is for complex number, 4 is for quaternions, and 8 is for octonions. There are no further possibilities. So for an algebra that is normed as well as division, in which you can define a norm, in which you can divide. So these are only 4 possibilities and no further. So these possibilities of division algebras are real numbers, which we have spoken about already, complex numbers, quaternions, and octonions. But if you allow the property that that you don't need to divide, so then we can also have Clifford algebras. So I mean, I will not say much about Clifford algebras, but just introduction to them. So thus even higher dimensional analogs are possible, but we need to abandon the division property. So then you have the notion of Clifford after the English mathematician Wilhelm Clifford. So one very important application or of the Clifford algebras, in spinors, in defining spinors in the Dirac equation for electron. So this is where it ends. So we started from natural numbers and our journey terminated at Clifford algebras. So this is the brief summary of what we talked about today. So we started with the natural numbers that were used for counting, let's say 4 sheep, 5 apples, 200 cows, 300 horses, etc., etc. But applications needed that we have to go beyond that. So let's say, so then we had to somehow invent or discover the notion of integers, rational numbers, even then real numbers, because not every polynomial equation had its solution in the real numbers. So we had to define the notion of complex numbers. So in a way, I mean, we sequentially went from R, which is real number, C, the complex number, H, the quaternions, and O, the octonions. So there is one way. I mean, I will not say much about this Cayley-Dickson algorithm. So Cayley-Dickson algorithm sequentially generates. Let's say you start with R, it generates C. You start with R, C, it generates H. In some sense of generation. So I mean, so I will not talk about Cayley-Dickson algorithm in this talk. And if you start with H or the quaternions, you get the octonions. So I mean, so the word of physics, it seems, somehow agrees to let it be described in terms of various numbers, as we have been seeing. So distances, of course, can be described in terms of real numbers, and Schrodinger equation contains complex numbers, etc., etc. So these are the references from where I've taken. So this is the main paper. So this paper came on the archive about 2 weeks ago, perhaps. Yeah, I think 2 weeks ago, 2 or maybe 3 weeks ago. So this is a very good paper to read, and this connects various, I mean, these kind of things, quaternions, octonions, etc., to the standard model. And from this book, Roger Penrose, The Route to Reality. So I thank you so much for your attention. Thank you very much. So I'll take some time for questions, for answering your questions, if you have any. Any questions?
For me, I am done.
Okay, good. Thank you. So
I also asked the question at that time only.
Okay.
Okay.
Fine. So,
But